Well, all right, here we are. So according to my records here, we finished chapter 3 last time, so we're going to start 4 today. But um, what we will need to do though is since 3 is done, next week, what I'd like to do is go over the chapter 3 problem sets, of which there are two. Let me just go open up Brightspace real fast so we can look at them. So, oh, so what we are doing here, we're going to have the chapter 3 problem sets. And the first one, as you can see, is really all about imaginary numbers, which is good. I think we're all getting pretty comfortable with that. And then the second part really covers everything else in that chapter. Let's see, let's just open it up real fast. So you can see, for example, we're going to be re-examining parabolas. Remember, we talked about the vertex form, the minimum, maximum points, the axis of symmetry, the domain and range. Then we looked at long division of polynomials, and we also took the inverses of radical functions. So that would pretty much cover all of the first 3 chapters, and then that means that we're ready for the sample midterm. Okay, now the sample midterm is meant to cover everything we've done up to this point to get us ready for the actual midterm. Now, if you're not sure, if you scroll down, it's way down here at the bottom, but it is here. And you'll see just by looking at it, there's a little bit of everything in here. The one thing that's different is these short answers. These are questions where the answer itself could typically be answered with a few words, maybe a number or an equation or whatever the case may be. These are concepts where it doesn't really justify a full problem, but we still need to understand these concepts. So the reason why they're there is because there will be some of these on the actual midterm, and so we could probably use some practice. Okay, so these first 12 are what we call short answers, and then the rest of these are the problems we've been doing all along. And you can see it really does go back to day one. We're talking here about relations and functions and domains and ranges, average rate of change, compound or composite functions, inverses, a little bit of everything. Yeah, if you once you get through this, you'll be ready for no matter what happens. And then once that's done, however long that takes, then we can start to decide on what date it makes the most sense to have the actual midterm. Okay, so probably it won't be next week, that's for sure. Maybe the Thursday of the week after or the following Monday, something in that neighborhood is probably about where it would make sense to have this midterm. So right now, for today, we'll just do a little bit of chapter 4, but then next week we'll focus our attention on the problem sets and on the sample midterm. Okay, and then we can have our test. Finally, get that out of the way. Now, in the meantime, we'll dive back into chapter 4, which is not on the first midterm. It's only in the second midterm. Now, it turns out that what we're doing here is awfully important for applied work. You'll see a lot of this in the physical sciences and in finance, and a lot of other disciplines lean very heavily on what we will call exponential and logarithmic functions. Okay, so we'll start with the exponential functions. I do want to point out that you've probably encountered this before, but maybe didn't you may not recognize the name. Definitely logarithms, though. You would have certainly covered that to a certain degree in certainly high school chemistry and physics. So some of this won't be brand new. Maybe some of it is, but at least some of this will not be completely new. So first things first, what exactly is an exponential function? All right. Now, what I'd like you to see here is that this is how an exponential function is written, and a and b can be any real numbers except 0. But what's unusual about this is that for the first time, if you notice, x is an exponent. Okay, up to this point, all the functions we've been considering were x raised to some power or other. Here, for the first time, x is itself the exponent, and that has a very big impact on the behavior of this function. So also A and B have their own unique interpretations. For example, A is what we will call the initial value of this function, or you can alternatively think of it as the intercept. Right there, that would be the point 0, comma A. A is the y coordinate of the intercept. So in other words, this is where it crosses the horizontal axis. And you can see why this has to be the case, because this is also f of 0, which is ab to the 0 power, which just reduces to a. So that's our quote initial value. For applied problems, let's say where we're dealing with time or money or whatever, um, we often find ourselves restricted to the first quadrant because that's where all the values are positive. Um, so you'll see as we go along that for some types of applications, we only need to consider the first quadrant. Now, what about the B? The B has a very important role. First, B is called the base. The reason why we're using the letter B is because it's the base. Okay, so whenever you have an exponent like this, remember we said that if you had something like this, 3 would be considered the coefficient. 2 is the exponent, and x is the base. So in other words, it's called a base because it is being raised to an exponent. And here, of course, that exponent is x. So b is the base, x is the exponent. Remember, this is the initial value. Although you can think of it as the coefficient in this case. B is the base, and x is the exponent. But it turns out the base has a very important it can be interpreted in a very interesting way. And what this is all about is this. B is equal to 1 plus the growth rate of x.
Who wants to make a decision?
I would love to know as soon as possible. Right. I would love to know, but I know that's not how the process works. Sure, before agency would be good. I want to do right by Justin as well. No one wants to live in gray. I know that's uncomfortable. I wouldn't want to be in that situation either.
Sweet Lou, there he is. How we doing, Lewis? Thanks so much for being with us. I'm gonna come right to you, dive right into it. Besides Chicago, Lewis, what team needs to get the quarterback situation right?
So I'm trying to figure out, oh, here it is. Okay, so now we know who is the guilty party. Yeah, when you come into a session like this, ideally you want to make sure your microphone is off because otherwise everyone can hear what's going on. We've had cases where you probably are aware that during the COVID, all of our classes were held online in this exact same format. And there were a few interesting cases where people did not know that the microphone was on. And let's just say they said things that maybe they would rather they didn't. So since we're not used to this, I just would like to mention again that everyone should ideally have their microphones turned off. Unless you want to say something, that's different. Also, there's a chat room up here where you can put questions and I'll see them. Anyway, let's get back to this. So yes, anyway, so what I would like to do is first show you an example, a graph. It's very difficult to visualize what this type of function looks like without graphs. Okay, so why don't we start with this case? We go to Symbolab. And we'll start with 3 times 2 to the x power. And we just want to see what it looks like. And you may be surprised to see, and now look at this. You can see it goes very, very slowly. And then all of a sudden it starts to increase very quickly. It cuts through the vertical axis. If you know, if you can see here, we know that at the vertical axis, x is 0, y is equal to 3, which should come as no surprise because that is our a. Right, let me just write this down somewhere. Okay, so in other words, remember we did say that if f of x equals ab to the x, this is our intercept. Which is often called the initial value. B is the base. So what that implies is that no matter what this function looks like, this 3 tells me that I can expect it to cross the vertical axis at the point 0, 3. Now, if you also look carefully, you'll see that leading up to that point, the function is actually growing very, very slowly. And then all of a sudden, it starts to really go nuts. It turns out very quickly. And I mean, really, look at this thing. If anything, it's getting steeper as x increases. So in other words, the slope is actually increasing as x increases. So the intercept point here could be written as 0, 3. And that's our function. Now, the only time I think you may have run into this in high school biology, you might remember if you were studying microorganisms like bacteria, that they grow very, very quickly. They may start out slowly, but a population of bacteria will eventually start to grow very, very rapidly. And in fact, their growth rate is often described as being exponential. And this is pretty much what it would look like. It just starts out and it just grows like crazy. Before you know it, you're overwhelmed with bacteria. And so this is a typical exponential function. Now, I want to mention a couple of other things here. First of all, based on, if you notice how Symbolab has these dashed lines, they want you to recognize that this is actually an asymptote. So the reason for that is because the function will never quite reach 0. And that implies, if you notice that the range is everything from 0 up to infinity, but not including the 0 itself. On the other hand, the domain, if you notice, there's no restrictions on x. There is no x. Oh, I see. Sorry, I missed this chat. Actually, when I record these sessions, it automatically takes attendance. So you're all set. Yeah, when it's over, I'll have a printout with all the names on it. So as long as you log in, I'll have your name. That's why I didn't actually call it out. I don't need to because it's being recorded by the system. All right. Uh-oh, another one here. All right. Now, the domain, on the other hand, is all the real numbers, as I started to say. There's no value of x, which when substituted into this function can lead to either division by 0 or an imaginary number. So as far as exponential functions are concerned, the domain is always the entire real number line. But the range in this case is everything from 0 up to infinity, but not including the 0. And as it turns out, this will always be true when a is positive. Okay, so in other words, if you notice, this is a, and this is b. A is positive, and when a is positive, that implies that the entire function will be above the axis, and therefore we'll have a shape like this. So if, on the other hand, I change it to -3 times 2x, sorry, 3 times 2 to the x, let's see what happens now. I'm sorry. I'm going to make that one little change. And you'll see what happens. Huh, it's been flipped upside down. Look at that. Okay, so in other words, what you're actually seeing is this. And now the horizontal axis is still an asymptote. But now A is negative. And so the range is different. In fact, the range is now everything from negative infinity up to, but not including zero. The domain hasn't changed at all. Okay. So think of this as like, imagine if I took the function on the left and just flipped it upside down with respect to the horizontal axis. That means that, and that's because of this negative here. Ah, interesting. Okay. And now, by the way, Simple Lab will tell us all this too. I mean, if you look up here, it's trying to be helpful. It's saying, listen, you probably are interested in knowing the domain, all the real numbers. The range, they've got it listed as strictly less than zero, which is what this means. The asymptote is the horizontal axis. There's no extreme points. In other words, it doesn't have a minimum or a maximum point. So that is what two typical exponential functions look like. Now, what I'd like you to see, though, is another interesting case, which I don't think I included in here. Let's try, instead of these, let's try y equals 3 times not 2 to the x, but 1/2 to the x. So you notice b is less than 1. Why does that matter? Because b is defined as 1 plus the growth rate, which implies in turn that the growth rate is b minus 1. And here, that's going to be 1/2 minus 1. That's a negative growth rate, which tells me that x is actually decreasing, or sorry, the function is decreasing as x increases. So let's see what that would look like graphically. Oh, that's interesting. Oh, because I still have the negative. Sorry, I forgot that. Okay. No, I meant it to be 3 times. I left the negative in by accident. That's why it looks wrong. Now we're talking. So you see what's happened here is that it's shrinking. It shrinks very quickly at first, and then the rate at which it shrinks is actually falling off. And again, we have an asymptote there. So now again, you notice we have an asymptote. The range is still 0 up to infinity. And that's because A is positive. In other words, the fact that we have B less than 1 does not affect the fact that A is still positive. So the mere fact that 3 for A is positive is why it stays above the horizontal axis. But it's the B being a fraction of 1 that causes it to fall off quickly rather than growing quickly. And then what I'm going to do is show you one more case. Y is negative 3 times 1/2 to the x. B is less than 1. A is less than 0. So what are we going to get now? Oh, and don't forget the domain is always positive to negative infinity. Okay, let's try this. I'm going to switch the sign to negative. Now, you know from before, it'll probably be a mirror image of what we just did. And yes, it is. As a matter of fact, if you look at it, it's going up. In other words, it's becoming less negative as we increase x. So that means the domain hasn't changed. The range is negative infinity up to 0. All right. So that pretty much covers all the cases you might run into. The others will be, they'll have different numbers, but the shapes will be very similar to these. And by the way, if you're thinking about an application of this one on the left, you might recall, for example, from high school physics, a radioactive isotope decays and turns into lead over time. And so the rate at which it does that actually follows what you're seeing here on the left. So anyway, this is what an exponential function is all about. So keep in mind, as long as you remember, A is the initial value or the intercept, B is the growth rate. And now you understand how the signs affect the results. All of these should make sense. Okay, now, here's a quick, simple introduction to this concept. What if we have two paintings in our collection? The first painting is worth $100,000 and it grows at a rate of $2,000 per year. So what this implies is that its growth rate is linear. And we can turn that into an equation very quickly and easily. What's different here, though, is that E will represent the passage of time, and that becomes our independent variable. Not X, but T. And the value of the painting as a function of time will be written as A of T, and that is now our dependent variable. So when you see the equation, you will not be surprised. In fact, let's jump ahead and show you what it looks like. Here it is. I'll just copy this back here for a second. Okay, so in other words, what it's saying is that, by the way, since this is the initial value, if you notice, this actually means A of 0. Okay, 0 means today. By the way, and as when we have a time variable like that, I just want to mention this, that 0 means right now or today. Then a number like, let's say 2 would mean 2 years in the future. 3 would mean 3 years in the future. So a 0 means today. So the current value of the painting is 100,000, which implies that A of 0 is 100,000. Because if you plug that in, you'll see that you'll get 100,000 plus 2,000 times 0, which is just 100,000. So that's our intercept. We're going to draw this as a straight line. This is the intercept. This is the slope. Okay, $2,000 per year is our slope. So in other words, if you were to try to sketch this out, it wouldn't be too difficult. In fact, let me try that here. It would be no different than any other straight line you've ever drawn, except T is on the horizontal axis, money, the dollar value, let's say, is on the vertical axis. Also, We only need to worry about the first quadrant because dollar amounts and time must be either 0 or positive. So here's our intercept. And the slope is $2,000 per year. And so this is what this painting's value does over time. Okay. Now we have another painting in our collection, painting B. Now, interestingly enough, painting B is also currently worth $100,000, but instead of growing at a rate of $2,000 per year, it grows at a rate of 2% per year. And that's a very different ballgame because now the growth depends on how many years have elapsed. Instead of a constant 2,000, the slope will actually increase over time. So this one, it starts out at 100,000 and then it grows at a rate of 2% per year. So this one can be modeled as an exponential function. Okay, so how would that work? So what I'm going to do first is replace the x's with t's. Now, this is the initial value. So I can rewrite this as f of t equals 100,000 b to the t power. Remember, b is 1 plus the growth rate. And the growth rate is 2%. So therefore, b is 1.02, and this ends up being f of t is 100,000 times 1.02 to the t power. So that's what that looks like. Okay, now what we really would like to do is see how they change over time. In other words, I want to know how the values of the paintings will change from one year to the next. So I've got a graph here that will do exactly that. Now, this is done in Excel, so it's not perfect, but think of it this way. So the blue line is a of t. This is our linear function. This is our exponential function. And so you can see what's happening is that over time, B is growing more quickly than A. And after a while, the difference between the two will be quite considerable. For example, in year 30, the difference between the two is, looks like it's about $30,000. And that will continue over time. So as more time elapses, the value of B will be growing more rapidly than A, and the spread between them will continue to grow. Okay, so this is the difference between a linear function and an exponential function. So you can see why this could be potentially so important in finance to help us understand how quickly our investments grow over time. It also could be important in biology to determine, for example, how quickly the plants in our garden are growing, or how quickly is the jungle growing, or, how about the population of wildlife? All of these could be modeled with exponential functions. Okay, so now we got some examples. Now, sometimes our interest in these cases comes down to the growth rate itself. We're interested in knowing how quickly something is growing over time, and we can solve for that algebraically. For example, what if we have, here's a biology example. In 2006, 80 deer were introduced into a wildlife refuge. Okay, so they've got all this open land and they're just running around all day. And 6 years later, the population is up to 180. Wow, that's fast. But deer, they have a very short let's just say that they reach maturity very quickly. So they go from 80 to 180. So what we want to know is, assuming that their growth rate is exponential, which is a perfectly natural assumption with a population like this, what is the implied growth rate? Okay. So here's what we have to think about. First of all, when it comes to time, we're not going to use the actual years. Okay, that would be very awkward. What we're going to do instead is this. If 2006 is the first year of our experiment, that will be t equals 0. Okay, remember, t is supposed to represent 0 for today, and then all the future years have a different number. Here, for example, 2012, because it's 6 years later, we'll call it 6. Oh. Another thing we're going to do is this. We're going to replace the x with t's, because now t is the independent variable. And then because we're trying to model the number of deer in our population, we're going to, and like, it doesn't matter, but we're going to call this n of t to remind ourselves that we're interested in n, the number of deer. Okay. So what do we know? Now this is a right here. This would be n of 0 is 80, which is a. We also know that n of 6, the number of deer in year 6, is 180. Okay, so that means so what I've done is I've replaced n of 6, this is 180, and then the t becomes 6 because we know that this is year 6. So what I'm doing is I'm evaluating my function at t equals 6. Now I can solve for b. Look how easy, well, it's not easy, but I can solve for it because I have an expression just in terms of b. So how would that work out? All right, here we go. 180 equals 80 b to the 6th. I divide 80 out of both sides. 2.25 equals b to the 6th. So how do I solve for something like that? Well, I don't want b to the 6th, I want b. So I'm going to raise both sides of the equation to the 1/6 power. Ah. So for this, you can just go to your calculator, or I mean, you could leave it like this, I suppose, but that would make it very difficult to find out the growth rate. So if you go to your calculator, what you're going to have to do here, by the way, is this. On the iPhone, this is what you would have to do. On the TI-84, you would just replace, it would be, say this is the iPhone. The button on the iPhone, I mean, the TI-84 is this one. And then instead of equals, you would type the enter button. Any way you look at it, though, 2.25 raised to the 1/6 power is approximately 1.1447. Okay, now here's the important thing to remember. B is 1 plus the growth rate. Which means that B minus 1 is the growth rate. And therefore 1.1447 minus 1, that's our growth rate. Which is about, it's about 14.47% per year. Okay, so that's how we're able to determine the fact that the deer population is growing at a rate of about 14.47% per year. So it's a question of identifying the A and the B. The A is just the initial value. The B is implied by the amount of deer that we had in the final year and the year in which this happens. Okay, so in other words, we do need two pieces of information to solve for these cases. It doesn't have to be two values of time, but we do need two pieces of information. So now, what about, now here's another example. This one is more an economics example. I think you'll find it interesting. What's happening here is that we found, let's say you went up to your attic one day and you found like this box with things that belong to your great grandparents. And in that box, we find an 1899 silver dollar. Now, just as a quick aside, just in case you're wondering, hold on one second. Yeah, look at that, the Morgan silver dollar. So a silver dollar is obviously worth $1 at the time, and it still is. It's just that now it's worth a lot more to collectors than $1. So you'd never see this in circulation. But God, even the silver content is probably worth at least $20. But still, if you look over here to a collector, this one in particular is worth $22.50. So now in our example, we're going to assume that our silver dollar is 37.42. Let's say it's in nicer condition than this one, and therefore it's worth more. Okay, this one's in pretty good shape, but it's not perfect, let's just say. 37.42. So we want to know what was the change in its value per year over that time period. Now, we're going to assume that the years we're looking at are 1899 when the coin was issued and 2019. So what do we know? So again, we're going to assume exponential growth. We're assuming that t is the independent variable. And this time we're going to use the letter V to represent value. Okay, instead of N, which represents the number of deer, we're going to use V, which can now be used to represent the value of the silver dollar. So what do we know? Well, we're going to let 1899 represent time 0, and 2019 will therefore be time 120. So we also know that V of 0 is $1 and V of 120 is 37.42. And that should be enough to solve for the growth rate. In particular, we know that this is A. So this function can be written as 1 times b to the t, or just very simply b to the t. We also know that v of 120 is remember, we were told that in 2019, the coin is worth 37.42. You know what that means? Then we can solve for b directly by taking the 1 over 120 power of both sides. So you're going to go to your calculator and raise this to the 1/120 power. And you're actually going to get 1 plus the growth rate, 3742 raised to the 1/120 power is, oh, I think I made a typo. There we go. 1.07. Let's round this to 1.0710. So B is 1.0710. Therefore, B minus 1 is the growth rate. So in other words, the coin's value increased an average of 7.1% per year over that time period. Which, it doesn't sound like a spectacular growth rate, but that's enough to double your money every 10 years or so. So that's not too bad. So if you sold this now to a collector, it would be represent a rate of return of 7.1% per year for 120 years. All right. So like I said, one of the many things that we can do with exponential functions is solve for the growth rate. Now, here's something else we can do. We can actually identify an exponential function from 2 points, just like we did with straight lines. Except that it's a lot messier. Okay, that's the only unfortunate thing. It's easy to do this with a straight line. 2 points, we find the slope, we plug one of them in, and we get the intercept. This is a little bit messy. Okay, so let's start with this case. Assuming that these 2 points are chosen from some exponential function, how would we find its equation? Based on the definition f of x equals ab to the x. So think of this as x1 f of x1, x2 f of x2. So let's see, let's plug these into the definition of an exponential function, starting with the first one, -2 comma 6. And let's see what we get. Okay, so you see what I've done. Remember, this is x, and this is f of x. So we end up with 6 equals ab to the -2 power. Well, that's not, I mean, you see what the problem here is, that you've got 2 unknowns and only 1 equation. So that means we have to do this with the second point and do the same thing. So that at the very least, we'll have 2 equations and 2 unknowns. Okay, so we'll do the same procedure with the second point. Okay. And now we've got 1 equals ab squared. Now that means we have that one, plus we already determined that 6 equals ab to the -2. So we've got 2 equations and 2 unknowns. Okay, but they're not linear functions. We can't, some of the techniques you've learned about solving simultaneous equations are not going to work here. What your goal to do here is this: find an expression for A substitute into the other equation. All right, so it sounds harder than it is. It's just, it's really more messy than anything else. It is messy, but it's straightforward too. It's kind of like, I don't know, making a cake. The end result is really tasty, but it can make quite a mess in your kitchen. Maybe you've watched your mother make a cake. You see what I mean. It just flour goes all over the place, and then there's sugar and there's all kinds of stuff going on, and it can be quite a mess. All right. Now, there's more than one way of doing this, of course, but why don't we try this? Let's start with this equation. And why don't I just solve for A? Okay. Divide both sides out. Or you can rewrite this as whatever that is, I can just plug that into this first equation. Ooh. Now keep in mind that b to the minus fourth is the same as 1 over b to the fourth. So I'm going to multiply both sides by b to the fourth. So you actually have here, oh my God, the fourth root of 1/6. Now that's kind of, like I said, it's kind of messy. But it's not a problem. So what do we do now? We can plug that into the first equation and solve for A. Now, by the way, in the slides, you'll see that I've taken this and written it out as this is approximately equal to 0.6389. In case you were wondering. Now, I can plug this back in, and actually, in principle, it could go back into either equation, and I'll get my solution for A. So let's do that. Let's put this into here. Only because it looks like it's a little simpler. You could pick either one. And if you do that, what do you have? So remember, we know that b is the fourth root of 1/6. We also know from the second equation that 1 equals ab squared. So that means we have 1 over b squared is a. Now, when you have something like this, keep in mind that what you've actually got is actually this, and then you're actually multiplying the exponents. So you've actually got 1 over radical over 6. And I've also gone through and determined that this is approximately equal to 2.449. So when you're done, you can write the equation with, exactly correctly. You can either write, for example, so remember A is, we just determined 1 over radical 6. And then B is equal to the fourth root of 1/6 raised to the x power. But if you want to use the approximate values, you can certainly feel free to do so. It's approximately 2.449 times 0.6389 to the X power. Either one is fine. Wow, what a mess that was. Oh my God. See, there's the only unfortunate thing about these exponential functions. They can get really messy in a hurry. And I mean really messy. Now, based on what you're seeing here, if you notice B is less than 1, so you should expect to see the graph look something like this. Okay. A is positive, so we stay completely above the horizontal axis, but the growth is negative. It's losing about 36% per year in its value. And so this is Excel's version of it. It's kind of like a car that's losing a lot of its value. I mean, depreciation is very, very rapid with this car. Okay, now we're going to introduce a very interesting application of all this, and this involves something called interest. Interest is something that will affect every aspect of your life going forward. And that's because it determines the cost of borrowing and the cost or the rate of return from investing. In the future, when you have money coming in, you will be both borrowing and lending. Okay, you'll have money in the bank. Hopefully you'll have stocks and other investments, but you'll also probably will have a car loan or a mortgage to buy a house or credit cards or something like that. And I know you have a student loan, so you're going to be borrowing and lending. So this is kind of important. So we're going to be looking at interest. Now, by the way, I just want to mention, in case you've never had an economics class, um, interest rates are very complex, but the Central Bank of the United States, which is known as the Federal Reserve System, or just the Fed, determines the level of interest rates in the economy. Okay, in other words, they have the power to raise them and lower them, which they do on a regular basis, depending on what's going on. The Fed lowers rates when the economy is weak and raises rates when inflation is rising too rapidly, or it's, in other words, more than the Fed would like to see. Okay, so now at the same time, though, the return to different investments depend on other factors, such as credit risk and maturity. For example, a bond issued by Apple stock is perceived to be very safe and therefore offers a relatively low rate of interest. If Tesla is perceived as being riskier than Apple, then its bonds will pay a higher rate of interest. Just like, and as far as your borrowing goes, borrowing ultimately depends on credit risk. So for example, a person with a very good credit rating will pay a lower rate of interest on his or her credit cards than a person with a very poor credit rating. So in other words, if and the same thing holds for other things too. This is also true of car loans, mortgages, et cetera, et cetera. In other words, really a lot of it comes down to the credit risk. So interest rates will heavily influence how much it costs you to borrow and how much you can earn from your investments. Now, here we want to focus on the different types of interest that are out there. When you earn interest, it can come in one of two forms, and when you pay it as well. First of all, the word principal in this context means the amount of money that's being borrowed or lent. So if I buy a car worth $50,000 and borrow 50,000 from the bank, that is the principal involved. Well, that would mean I'm doing rather well. If I, let's say, put $100,000 in the bank, that is also called principal because that's the amount that I'm lending. The interest that's paid directly in the principal is called simple interest. And the interest on the interest that accumulate over time is known as compound interest. So we always have to make a distinction between these two. Simple interest is interest just on the original principal. Interest on interest is called compound interest. Now, this all sounds very abstract, but when we do a few examples, it'll start to make sense. Okay. So how do we figure them out? Okay. Well, first, imagine yourself putting money in the bank. And you want to know, of course, how much you'll have in the future. Let's say you put money there and the bank tells you how much interest they're paying. You would like to figure out how much you'll have in the future. The whole point of putting your money in the bank is to earn interest. So, of course, there's a helpful formula that will let us calculate this directly. Now, it looks terrifying, but it's really not that bad. So, what you're seeing here, this formula tells me first, A is what we call the future value of a sum. In other words, if I put money in the bank, what will the sum be worth in the future? That matters a great deal if you're saving for something specific, like if I'm saving to make a down payment on a house, or if I want to retire or whatever. It's very helpful to know how much money I can expect to have in the bank in the future. That's what A means. P is the original principal that I invested. R is the annual rate of interest. Which, by the way, is a percentage. Although we express it as a decimal in these formulas. T is time in years. Now, this N requires some explanation. The name of N is compounding frequency. What in the world does that mean? Okay, that's the part that we have to discuss. The rest of it is pretty straightforward. I mean, when you walk in the door of the bank, they'll tell you what interest rates they're paying are, is whatever they pay. T, you know how many years you want to put your money in the bank or how many years you want to borrow. P is the amount of money you have to lend or you want to borrow. Now, N is a very interesting idea. So think about this. Suppose that a bank pays an annual rate of 6% on its savings accounts. It doesn't, but let's just say it does. Here's the important part. If the bank pays the entire amount at the end of the year, this is referred to as annual compounding. Okay, they wait to the end of the year, they see how much money you have, they give you 6%, and that's what we call annual compounding. But what if they do this? If instead the bank pays 3% at the end of 6 months, and then another 3% at the end of the year, this is known as semi-annual compounding. Semi-annual meaning twice a year. Interesting. In other words, instead of waiting the full year to give you 6, halfway through they give you 3, and then halfway through another 3, or at the end another 3. Interesting. And then what if instead you can start to see where this is going. There's so many possibilities. Every quarter, which is 3 months. This is known as quarterly compound. If the bank pays 0.5% every month, which still adds up to 12%, by the way, this is known as monthly compounding. So it's still 6%, they're just distributing it differently. And then finally, what about this? If the bank pays, it would be 6% divided by 365. Oh my God, what is that? Hold on 1 second. That would work out to 0.01644% per day. This is known as daily compounding. Now you may wonder, well, does this make any difference? Good question. That's a very good question. The answer is yes, it does matter a great deal which one of these approaches the bank is taking. So in our formulas, the way it works is this. N is the number of times per year that the interest is paid. So actually, let me add a couple more in here. Since I left out 1 or 2. That doesn't go there. Okay, so in other words, those are the only ones you're likely to run into in practice. If it's paid once a year, it's n equals 1 in that formula. Twice a year means n equals 2. Quarterly is 4 times per year. Monthly is 12 times per year. Daily is 365. So that number is what goes into that formula. Remember, you saw it before. It was A equals P 1 plus R over N to the NT power. Okay. Now, that raises an interesting question. What effect does this have on our results? Or does it even matter? Why do we even think about this? What's the big deal? Well, the way it works is this. Okay. I'm waiting for it to save. Here we go. The higher and the greater will be the future value, which is A. Okay, so in other words, for a saver or investor, a higher N means earning more interest. For a borrower, meaning somebody who's using their credit card, a higher N means paying more interest. So if you're the borrower, you want N to be as small as possible. If you're the lender, meaning you're investing your money, you want it to be as high as possible. Now, by convention, I'll just mention this right now, for the most part, interest rates are compounded daily. Not always. There might be some exceptions, but for the most part, if you go to the bank, for example, and start a savings account or a checking account, or if you get a credit card, for example, or if you borrow money to buy a car, anything like that, you'll discover that the interest is being compounded daily. Okay, so that's if you're the borrower, that's bad news. If you're the lender, though, the person who's saving his money, that's good news. Okay. Now we're going to see as we go along how much of a difference it makes with our rates of return and our borrowing costs. Now, we're going to introduce a formula for calculating simple interest first, and then we'll focus our attention on compound interest. So simple interest is principal times rate times interest. Let me write this here. Okay, so simple interest, meaning interest on principal. This is our principal. This is our annual rate of interest. And T is time in years. Now, here's an interesting point. If you look at that formula, the one thing that's missing is N. Okay, so I want to point that out to you right now. Simple interest is not affected by N. Only compound interest is affected by N. So that'll help explain what's coming next. Simple interest is some amount that has nothing to do with N. Compound interest is directly impacted by N. Now, also, for our strategy for calculating, since we have a nice, easy formula for simple interest, calculating compound interest is fairly complicated. So this is the strategy that we'll use. If you recall, we said that all interest is either simple or compound. Which implies that compound interest equals total interest minus simple interest. So our strategy will be to calculate total interest and simple interest, and the difference will represent our compound interest. Okay, so that won't be that difficult. Trying to come up with the compound directly would be very messy and challenging. So instead, we'll do it this way. All right. So now I think it's time for an example. Let's say, actually, let me leave that there for a second so you can catch up. And then we'll do a numerical example. All right, here we go. Let's look at an example. First things first, $10,000 is borrowed for 3 years with an annual rate of interest of 6%, compounded monthly. That means that n equals 12. How much interest will the borrower pay during the lifetime of the loan? Okay, so that's an interesting question, something you'll run into in the future. And so in other words, when you're done paying this back, you'll pay back the $10,000 plus the interest. The question is, how much will the interest cost you? So keep in mind, now we're going to gather up the data that we have. P is 10,000. That's the amount we borrowed. That's our principal. R is 6%, meaning the annual rate is 6% that we're borrowing at. T is 3 years. It's a 3-year loan. And 12 is the monthly compound. In other words, the fact that it says 12 here means the interest is compounded monthly. That's okay. So that means we can go and figure out first how much will we pay back to the lender. And for that, we need this formula, future value formula, which is A. That is how much we'll pay back over the 3 years with our monthly payments. So if you plug in all these numbers, here's what you might want to think about doing. If you notice, I've reduced this ratio to 0.5%, and then the exponent was simplified to 36. So what you probably should do here is do this part of the equation first. And whatever that is will be multiplied by the $10,000. So let's do that first. 1.005 raised to the 36th power is, hold on. Make sure it's 005, by the way, be careful. It's approximately 1.19668. And now you can multiply that. Actually, it's 1. All right, that's fine. Then you multiply it by 10,000 equals, and you only have to round enough to get to dollars and cents. 11,966.81. That's how much is going to come out of our pockets over the next 3 years. Okay, this is the future value. If we had put $10,000 in the bank instead, this is how much our bank balance would have been in 36 months or 3 years. Now, clearly, the principal was $10,000. So how much interest did we actually pay? It would have to be the difference between the two. Okay, so in other words, we paid this much, we borrowed this much. This is our total interest. And that's fine, but now we want to break it up further into simple and compound interest. Okay. So we have our total. We want to break it up now. But remember, there's a very easy formula for simple interest. So we won't have any trouble with this. And that formula was PRT, I equals PRT. We borrowed $10,000. This is the monthly rate of interest, by the way. And this is the number of months. That equals 1,800. Well, that means that if we paid a total of interest of 1966.81 and 1,800 of it was simple interest, then whatever's left over must be compound interest. So you can see we're doing this in stages. Okay. There really isn't a realistically useful formula for directly calculating compound interest. It's easier to just do it like this. In other words, we figure out the future value, the amount we paid, figure out how much interest is paid, subtract off the simple interest, and then what's left over is the compound interest. So that will be the approach that we'll take. Okay. So now what's interesting about this is that the simple interest was a lot larger than the compound interest. That's because it's only a 3-year loan. Okay, I just want to mention this. Over time, a compound interest grows much more quickly than simple interest. So for a longer loan, the proportion of compound interest will be much higher than what we saw here. And eventually, there will be more compound interest than simple interest. We'll see that as we go along with our examples. Okay. Wow, we really zoomed through this thing. Anyway, so as I've mentioned many times before, I don't like to let the classes get too far apart from each other. The morning class isn't quite at this level, this point just yet. So, here's what I'd like to do. Let's stop it here. And what we'll do the next couple of times we meet is we'll work on the 2 chapter 3 problem sets and then the sample midterm. And only when they're done will we get back to this. And then we'll of course have to review it a little bit, but then we can pick a date for the exam. And when that's done, then we can just dive right back into this. So between now and Monday, what you should do is download the chapter 3 problem sets and work on them. And make sure if you understand it, you're fine. If not, bring your questions with you on Monday. And then if you're really ambitious, you can also work on the sample midterm. Okay, so probably this will take up all of next week, the problem sets in the sample midterm. Okay, so that's where we're heading for the next week or so. So anyway, I'm hoping that I'll be back to normal by Monday. So I'll see you then. Unless you hear from me, we'll be back to the classroom next Monday. Okay. So yeah, I can tell already I'm feeling even better than I was this morning in my 8:30 class. It may not sound like it, but I definitely am. So I'm pretty sure I'll be ready by next Monday. So, all right. In the meantime, if you don't have any last minute questions, I'll just see you all next week. Yes, thank you. All right, I'll see you all next time. You're welcome. Bye.